Our final presenter for this morning is Nicky Fox. Please join me in welcoming Nicky.
Good morning. I always hate being the final one because I'm standing between you and lunch. And judging by all the fantastic presentations, there's an awful lot of great stuff to see. And so I am Nicky Fox. I am the director of NASA's heliophysics division. And a lot of people ask me, what the heck is heliophysics? And it is indeed a word we made up. And it means basically everything that is affected by the sun. So I like to tell my kids, I'm the Lion King. I have everything the sun touches. So I'm going to tell you about a wonderful mission that we actually launched last year to go and study our most important star. And so it was a beautiful phrase that was used yesterday by Jonah Nolan, where he said, you know, we stand in the time before. And so I want to take you back to the time before we were able to do this amazing mission. So let's take you back to 1958, the very beginning of the space age. And of course, you recognize this young man as James Van Allen. And here he is holding up Explorer 1, which of course gave us our first real discovery that space wasn't empty. The same year, 1958, a then young scientist by the name of Dr. Eugene Parker published a paper. This paper was very controversial at the time, and in it, he predicted that the sun's outer atmosphere would be continually accelerated away and would actually bathe all of the planets. A lot of people didn't believe him. In fact, one of the reviewers most unkindly said, if you're going to publish in this type of subject, you probably should go to the library first. Fortunately for us, the editor said, well, golly, this is so controversial, we should publish it. In talking to Gene, he said to me, all I did was solve a few equations. It was very simple. So obviously his definition of simple and mine are a little bit different. But anyway, forging ahead, we decided that this was a good theory to follow. And just a few years later, using data from Mariner 10, it was discovered indeed that this atmosphere was continually accelerating away, and we call it the solar wind. So if we look closely at the sun, and at this point I disappear into the background of my thing, but if we look closely at the sun here, you see all kinds of beautiful features. Sunspots, active regions, every different way we look at our sun, all different wavelengths, we see different features. And so the sun is anything but constant. It may rise every day and set every night, but boy, it changes. You see a lot of this big activity, these coronal mass ejections, sending billions of tons of coronal material traveling at millions of miles. And this, of course, is the home of the solar wind, this continually flowing outer region. And not only is this a mystery, like why is it continually accelerating? But in fact, if you look at the sun during one of those beautiful total solar eclipses, you see that the hazy region around the sun, so this corona that's now visible, that plasma, that material itself, is about 300 times hotter than the surface of the sun. And that really just doesn't make sense. Now, you can imagine we're scientists. We have a million different possible theories for how this can happen. But so far, we haven't been able to test any of these theories. We haven't found one that holds up to every different little condition. And so the only way that we can actually test these theories is to bravely send a spacecraft right into the atmosphere of the sun. Now, I mentioned 1958 was the first time that people said, gee, we should do this. We should send a probe into the sun. And it has taken 60 years of careful observations, careful planning, and a lot of honing of technology to be able to allow us to fly this very, very daring mission. So let's take a look at some of the technology behind the mission. So the first thing is we're very small and very, very light. We used to always joke that we were the mission that was always on a diet, because if we put on a pound, it would probably kill the mission. So we're extremely small. The spacecraft she stands at about 3 meters tall from stem to stern. At her widest part here, that's the heat shield, which I'll talk about in a minute. That's about 2.3 meters in diameter. But the bus itself is only about a meter in diameter, so extremely small. Here's just a nice image here showing just the outside of the bus with no instruments or anything attached. Here with the doors open, you can see the fuel tank in the center there, the propulsion tank, and all of the harness that is basically the nuts and bolts, everything that we need to fly the mission. And so you can see how crowded that is, and we don't have anything in there yet. The reason we have to be so small, despite having a Delta IV Heavy and an upper stage, a custom-built third stage for us, we have to be thrown away with incredible energy because we do not want to be in any way influenced by the Earth. So as the Earth is rotating around the sun, we do not want to be dragged with the Earth. We want to go straight to the sun. And so we meant that we needed an incredible C3, an incredible amount of launch energy. So we made ourselves as small and compact as possible and then sat on the top of that mighty Delta IV. If I show you a little bit about our thermal protection system, our heat shield. So I mentioned it was 2.3 meters in diameter. That's about 8 feet. I have a piece of it over there. I'm just going to show you in a second. But before I show you the actual material, you see here the truss that it's standing on. That is a titanium welded structure that was custom built for Parker Solar Probe by a company in Ohio that have never worked in the space business before. They actually did nuclear welding, but they were the only company to take up the challenge of doing this kind of custom welding, because you can imagine how difficult it is to hold this heat shield on. The heat shield is held with just 6 carbon bolts. And the reason we don't hold it with any more, we don't want any heat from that heat shield convecting into the spacecraft. And so it's held with 6 carbon bolts, and you see a lot of different nice pictures of it. If I play you a quick movie, you'll see our heat shield lead. Betsy here is heating one side of the heat shield. She'll get it up to just a couple of hundred degrees. We're actually at about 2,500 when we're on orbit. But as you can see, it's glowing red here. And our extremely brave safety engineer, Curtis, on the other side. If I had the sound on, he would be reporting to you that that is completely cool as she is heating that side. And so if I show you, it was like a bit of show and tell. This is a piece of our heat shield. So as I said, the real one is about 8 feet across. So we lovingly call it our 8-foot frisbee. So this is one side of the heat shield. It's made of a carbon-carbon composite, very similar to the epoxy that you might find in your golf clubs or a very nice tennis racket. This is one of the attach points called a pie pan, and so one of the carbon bolts goes through this structure here. If I turn it so you can sort of see edge on, in between that phase sheet, there is some carbon-carbon foam. It has the texture a little bit like florist foam. And thank you very much to everybody who cleaned my heat shield for me last night. On top of that, there is another layer of the carbon-carbon, so two of these phase sheets, essentially. And then on the top is our custom-built, or custom-made, I should say, whiter-than-white coating. So it's an aluminous plasma-sprayed coating. And a bit like a ceramic coating, and that was designed just for Parker Solar Probe. And so one of the things that we say is, so I mentioned that the plasma in the corona is about 3 million degrees, but you'll notice on that chart, I said that the front of this only gets up to 2,500 degrees Fahrenheit. And that, of course, is because that atmosphere that the spacecraft is flying through is not very dense. And so if you think of turning your oven on and setting it at 450, you can put your hand in, you won't get burnt, not unless you touch a rack. So unless something couples into you, you don't feel that intense heat. And so most of the heat that Solar Probe has to deal with is from the photons, from the light from the sun itself. So this whiter-than-white coating actually reflects a lot of that, so we don't have to deal so much with any of the heat. So front side of the heat shield, 2,500 degrees Fahrenheit. Instruments that are on the main body of the spacecraft, about outside today, about 81 degrees. And so why the white coating? That kind of makes sense if you think of, see if we can play it, here we go. The difference in a white car on a hot day and a black car on a hot day. I'd choose the white one, always much, much cooler. So one of the other challenges that we had to do was not use any kind of nuclear power system. So no RTG, we actually had to use solar panels. And I am sure you're sitting there thinking, well, you're going to the sun, what is the big deal, hey? So as everybody knows, if you leave your iPhone on the front seat of your car on a hot day, yeah. Solar cells, electronics of any kind, do not like to get hot. So the big challenge, we're going into this region, we're getting up to these incredible temperatures, is how to keep our solar panels cool. And so here's just a shot of one of the pieces of our solar wing. So much like some of the robots you've seen, they can actually go out and they can flap and feather as necessary. Here you see it at full stretch. So it's getting the maximum amount of solar power onto those wings. What you're looking at up here is that very last sort of articulated piece. My pointer doesn't appear to be working very well today, but this piece here is what you're looking at in that upper picture. And when we're very, very close to the sun, we've tucked those wings all the way in, and so it literally is just the fingertips, just that very last layer of cells actually produces the same amount of power when we're close to the sun as the entire wing does when we're far away. So we also flow water through each of these solar panels. They have kind of like veins flowing through them, and water flows through them all the time to make sure that they stay cool. And that titanium structure that I showed you that is holding the heat shield in place also has all of the radiator fins on it that are actually used to get rid of the heat from the water that is cooling our solar panels. And so here is just a nice little shot of Parker's solar probe spreading out her solar wings to get the maximum amount of sun she can, and then coming into closest approach, tucking them away behind her so that very little gets seen. I'll also point out another big challenge for us was the autonomy. She is the most independent spacecraft to ever fly. She is traveling at a blistering speed, and it takes light 8 minutes to get from the sun to the Earth. So if she has a problem, we do not have time to joystick this mission. She has to look after herself. So an incredible, incredible amount of work went into placing sun sensors that always need to stay in the shade, and then doing all of the, the what-if scenarios on that spacecraft before launch to make sure that whatever happens, she can right herself. And so I just want to show you now a video of us building the spacecraft. So here is Felipe putting together the first structure, the main body, dropping in that harness that I showed you, and there's the propulsion tank, dropping the upper deck onto the bottom of Parker's solar probe. So she finally, to us, looked like solar probe. There they are bonding the bottom face sheet of the heat shield onto the foam. And they've got about to start putting the top sheet on. This is the most terrifying sight I've ever seen, vibing the spacecraft. It makes a terrible noise, and it's not good for people to watch. Here we are. Here's another terrifying sight as we lifted the spacecraft 4 stories high and lowered her into the vacuum chamber at NASA's Goddard Space Flight Center, where she had all of her testing done. A few weeks later, we flew her, courtesy of the US Air Force, on a C-17 down to Florida. She was at Astrotech for a number of months doing final testing and integration. Here you see them putting on those solar panels. Obviously, they're in their protective case right now. The heat shield going on top, kind of giving solar probe her crown as they lowered the heat shield on. And you can see there those 6 pipe pans with the bolts, and now nice view of that whiter than white coating. As we're getting really towards launch, we lifted the spacecraft and installed her on top of our custom-built upper stage. And there she is inside her tricked-out 40-foot Delta IV fairing, looking very, very beautiful. And here now she's out on the launch pad. And incidentally, the spacecraft on the logo is about the size of Parker's solar probe. She is tiny. She looks like a hood ornament on the top of a Delta IV Heavy. So let me show you, just before I show you the launch, you see the bright spot over here? This is actually the planet Venus, and that was very important for us. It was sort of a really nice moment the team shared as we realized that once she left Earth, her first stop was actually Venus. And so there is Venus just there by our launch site. And so I will show you the launch. Still brings me chills every time I see this, but here we are, August the 12th. 2018, 3:31 in the morning. as our mighty Delta IV lifted off the launch pad, taking Parker Solar Probe into space. It was a perfect and extremely beautiful launch. Shortly after getting out of the atmosphere, the fairing opens and out comes Solar Probe. You notice there the cryogenic second stage, and she'll separate from that. And then that custom-built upper stage will fire, giving her about 80% of her total delta V, by the way. Shortly after that, she separated and started to free fly in space. The first thing we do, obviously, is put out those solar wings, as I just talked about, to make sure that she's got enough power. Then we'd start to deploy anything that was kind of tucked away for launch. So there's the magnetic field boom at the back, and here come the electric field booms opening up here. So she's moving very fast. As I mentioned, a lot of launch energy. Just 7 weeks after launch, she encounters the planet Venus for the very first time, where she does her first Venus flyby, which is helping to sort of turn that orbit. It's a little bit like doing a handbrake turn around Venus, and it focuses that orbit so it comes right in close to the sun. We do this type of petal orbit 24 times over the 7-year duration of the mission, and she will fly past Venus 7 times total during that time, each time making that orbit just a little bit closer until she is right up extremely close to the sun. And there she is. And you'll notice those solar wings completely tucked back behind that heat shield there. So if we take a little bit of a look at our Venus flyby, we're not like those other planetary missions that take energy from a planet. We give to Venus. We actually use Venus to slow down a little bit. As I mentioned, a little bit like a handbrake turn. It really focuses that orbit in towards the sun. And you'll see when she comes out of that first orbit, the orbit is much smaller. So as I said, 7 of those maneuvers during the 7 years, allowing her to get closer and closer to the sun. So we're not competitive at all. We're just faster, hotter, and closer than anything else has ever been. And so when I say we broke speed records, we broke a lot of speed records. So we're already the fastest human-made object. We broke that record on October 19th when we traveled at about 153,000 miles an hour. And we're also obviously the closest. Hottest, I've already talked about that. We're in 3 million degree plasma. We have components on the spacecraft that are up at about 2,500 degrees. What I didn't mention actually was just the challenge of the temperature changes. We get very hot, but we also get very cold when we're out around Venus. And so finding materials that will go hot and cold to those extremes multiple times is really hard. If you think of any material you heat it and cool it continually, it'll change its properties. So we can't do that. And then closer. So at our final closest approach, we're at about 3.9 million miles above the sun's surface. And somebody commented to me at dinner last night, well, that's not very close. And so I said, well, let's put that into perspective, shall we? We're 93 million miles away from the sun. So if I put the sun and the Earth on either side of a football field, I'll put a couple of celestial objects in there to orient you. So there is Mercury at the sun's 35-yard line. Venus would be at the Earth's 28-yard line. Some of these beautiful coronal loops that we see can stretch out as far as the 15-yard line. Now, up until Parker Solar Probe, Helios 2, which was a NASA German Space Center joint mission, that had gone in as far as the Earth's 29-yard line. But now, if we welcome to the stadium the newest kid on the block, Parker Solar Probe will tuck and run to the 4-yard line. So definitely in the red zone, knocking on the door for a touchdown. So I think that's pretty close. All right. So we call her Parker Solar Probe. It's a very momentous thing for us to carry this name. You see here the commemorative plaque that we put on the side of the spacecraft. Many of you may have signed up last year to get the hottest ticket and have your name put on that SD-RAM card. But of course, it also carries some pictures of our namesake, Gene Parker, and most importantly, his seminal paper. And now this is a really big deal that you may not realize, but this is the very first time that NASA has ever named a mission after somebody during their lifetime. If you add into that, it's extremely rare to get a NASA mission named after you anyway. You have more of a chance of getting a Nobel Prize than you do of having a NASA mission named after you. And so to have it done during your own lifetime is a bit special. And so I was delighted, as you'll see by my beaming face in a minute, I was delighted that Gene and his family joined us at the launch site to actually watch his legacy mission lift into space. So you can only imagine how excited I was. And at 4:13 in the morning, God love him, Gene let me take a selfie with him. So it's a really big deal. And you can imagine how excited I am to tell you he's in the room right now. So ladies and gentlemen, please join me in welcoming Dr. Gene Parker. And Gene will be around for the rest of the day. He'll be at the dinner tonight, so do stop by and say hi. And now I'm really wondering how on earth I actually have anything else to show you after showing you Gene, but I do. I do. I am going to show you some data that just came down from the spacecraft that no one has seen before. So right before I do, let me tell you just a little bit about the instruments so that you kind of understand what I'm going to show you. So we already did most of the spacecraft. I'll just note that high gain antenna and where it's located actually gives us challenges on bringing down the data, because anytime the heat shield is in the way, we can't talk to the spacecraft. And so again, more trauma and drama about doing our flybys. But anyway, you see Sweep SPC at the top there. That is a Faraday cup. It's a very simple instrument, but it's actually out in the full environment. I always think of her as the bravest little instrument on the spacecraft, because she doesn't take shade from the heat shield. She peeps around the outside, and she's in that full solar environment. I will point out Sweep Span B. If I flip over the spacecraft, you'll see Span A+. They're sister instruments. Their fields of view fit together like the seams on a baseball, and so it gives us a full 360-degree view of the solar wind, which is very important to us, as you'll see in a minute. The ESYS suite, they are looking at the high-energy particles, so particles that are associated with transients in the solar wind, like a shock, or a coronal mass ejection, or a big solar flare. You saw the Fields magnetometer come out in the video. We have 3 magnetometers on Parker Solar Probe. We know that the field is going to vary dramatically as we go in and out of our orbit, and so we need to cover the full frequency range, so we have 3. And then last but not least, our Whisper camera, our white light imager, that is taking pictures of the corona and the solar wind right in front of the spacecraft. So this is where we were a few days ago. We're actually at about half the distance to the sun to the Earth right now, and we're traveling at a mere 200,000 miles per hour. I know it's really slow. When we come to our closest approach, we're traveling at 430,000 miles an hour, which is about 118 miles a second. One of the things that's nice about this plot, as I said, we're actually about here right now, but you can see at this point, we'll do another Venus flyby, and then that orbit gets smaller, and so we sort of walk in until we get to our final thing. And so I have to ask for no photography, because out of respect to the scientists who have given me their data and have not published it yet, so I'm going to ask for no photography for this piece. So here we see Whisper. This is the images taken during our first closest approach. These just came down about 2 weeks ago from the spacecraft. I'll just point out a couple of things. In this one, you can see Jupiter and anti-Jupiter. This is a difference image. The images are taken just 12 hours apart, so it gives you a really good idea of how fast we're moving when Venus is moving that far in our field of reference. You can see a couple of very small features here, very close up to the sun, magnetic flux ropes. They are not visible from the Earth, and nor are they visible from any of our observers that are out at the L1 point or out in the solar wind, mostly because they have to look through the atmosphere. It was just like Sebastian was talking about earlier. It's very hard to see things when you have to look through an atmosphere. We're now inside the atmosphere and able to look at these incredible features. Gene himself has a theory for the coronal heating involving very small nanoflares. And so we're excited to start seeing a lot of these little features that are small and short-lived, which may indeed be a sign of the nanoflares. Over here, you see a stationary region that is extending to the 10-yard line on our football analogy. And so pretty soon, Parker Solar Probe will be inside that region, really flying through some of these incredibly intense areas. This is just a very fast-moving video that Russ Howard, the PI, sent me. It's 23 different images, and it is taken around our perihelion, which was November the 6th. And so already you can see a lot. You can see a lot in there. There's a lot of dust. It's a very dusty region close to the sun. You can see cosmic rays. You can certainly see the planet Jupiter whizzing across. And then that sort of big puffy area that you see on the edge there, and that's actually our Milky Way. And it's the beautiful images of the Milky Way that we've been taking with our coronagraph. So there is the approximate size and location of the sun compared to what you're seeing. And so obviously the closer in we go, the more we will continue to get down to the sun's surface. This is some data from the high energy particle suite. And so where you see these sort of red bands, that is where the spacecraft is encountering these transients. So a lot of these very close-in magnetic field structures that you saw in the WISPR image moving out and then hopefully impacting the spacecraft. I always get asked the question, are you worried that when you're close in, a giant storm will happen? And I usually say, no, I'm more worried that it won't, because we've designed ourselves to see these amazing structures. And so having a quiet sun is not what I want to see. And so this plot was actually shown at the American Geophysical Union in December and got gasps, audible gasps from the audience. Yeah, we're geeks, I know. So we can gasp over anything. But at the top here, you're looking at some magnetic field data. The white line there really represents the total magnetic field coming from the sun. The red line actually gives us an illustration of the direction that it is flowing radially. And so right now it looks like it's flowing away and towards and away and towards and away and towards. And so with the other plots, the density and the velocity didn't really show us anything amazing. And so we just thought, oh, we must be close to the heliospheric current sheet, this region where we sort of transfer from flux that's pointing in one direction to flux that's pointing in another direction. We must just be going up and down on that current sheet. But a few weeks ago, we downloaded the data from our SPAN instrument. And so now what we see is we look at these electron pitch angle distributions. And so essentially, when you see a big change in where these electrons are, if they're up towards 180 or if they're down around 0, that is telling you that we have a major turn in the whole structure of the magnetic field. And so instead of us thinking that we're now bobbing up and down across the heliospheric current sheet, we can see that there's one reversal here and another reversal here and one at the very end there, which means that we've only crossed it a couple of times. So now what we're seeing is that this is truly a magnetic field that is kind of looping in and out, a bit like a whip crack. So it's coming out from the sun and then reversing back in again, the plasma staying on those field lines. And so that's an extremely interesting result. It was not what we were expecting to see. You'll see here, obviously, with the blocky data at the end, we haven't got all of our high-resolution data down. But the more data we get down, the more excited we are to see what's going on. And so that's just a taste of what Parker Solar Probe has seen on her very first orbit. Also, you'll notice at the top a CME, a coronal mass ejection. There's one there, and there's one just here. We were hoping to see a couple during the 7 years. We've seen 2 on the first perihelion. So we're a very happy science team right now. And so I will finish with just sort of putting this a little bit into perspective. I mean, obviously, we're scientists. We get excited about wiggly lines. But the sun really does govern everything that we do here at Earth. It powers the very beautiful aurora Of course, the aurora is a current system in the sky, and when you have a changing current system in the sky, it can indeed cause problems for things on the ground, like pipelines, like power grids, like undersea cables, things that can be very, very susceptible to continual changes. In fact, if we look at almost every piece of technology that we rely on, it is all susceptible to space weather, to weather that is driven by the sun. So whether you're an astronaut out doing a spacewalk, whether you're a spacecraft that is in or avoiding the Van Allen radiation belts at the time, passengers going on polar routes, everybody is very, very interested and very worried about what space weather can do. And in fact, the Heliophysics division is charged with doing the science research to better enabling the prediction of space weather. And of course, this is particularly important now as we stand on the verge of the golden age, as Jeff coined at dinner on Saturday. We are starting to be in a time where long-duration crew missions, where we will be leaving the protective bubble. And so missions like Parker Solar Probe that are actually explaining what is going on at our star have big impacts as we move beyond our solar system and start going to travel to new stars and look for new habitable worlds. Understanding how these stars work is really, really key to everything we do. And so I, for one, cannot wait to see what happens next. Thank you very much for keep looking up.